Hello everyone and welcome back to the channel. I know I haven't been posting videos lately, but I'll try to catch up, okay? So last time we solved general problems for grade 6 curriculum, and I think we've covered all the topics. So today we are going to start with grade 7 material, and as you will see very shortly, the topics get progressively more and more abstract. Okay, there won't be that many games, millionaire games. I'll be focusing more on full lessons from now on because it's heavy theory, guys. So let's start with the first thing, and that is the monomial. Okay, the monomial is the basic building block you can think of, the basic building block of algebra. All right, so the first thing when we want to discuss when we speak about the monomial is what is algebra, what is the difference between arithmetic and algebra. So this is going to be our first point of today's presentation: arithmetic and algebra. And I will just write my basic understanding. So arithmetics is a section or part of mathematics which studies various types of numbers. You know, we have natural numbers, negative numbers, fractions. In grade 8 we'll encounter irrational numbers. In grade 12 we'll encounter complex numbers, and so on and so forth. So we have various types of numbers and the operations with them. The operations we can perform with those numbers, like addition, subtraction, multiplication, division, putting the number to some power, etc., etc. Okay, so basically when we study arithmetics, this is the more basic branch of mathematics. Here section, branch, you can think of it as a branch. We are just learning how to calculate. Okay, if we want to calculate what is 3 times 5, we are studying arithmetics. If we want to know what is 5 plus 7, okay, or 60 divided by 4, this is arithmetic. So as children, for example, when we want to figure out if we give a $10 bill to the grocery store, and our bill is like $5.50. okay, how much change should we get? So we have to subtract 10 minus $5.50. We are expecting $4.50 of change. So this is how we operate with arithmetics on a daily basis. When we want to make some calculations, this is arithmetics. Okay, now algebra a branch of mathematics in which numbers are replaced with letters and which studies general formulas, let's say. Okay, let's just write it in this informal way. So if we want to know by which formula are we going to calculate something when we are doing algebra, okay? Because we're not concerned about concrete numbers. We are concerned if we plug in some numbers, they can be any numbers, how are we going to find a certain variable, okay? We're going to speak about constants and variables in just a second. But in order to make this point home, I'll give you a concrete example, okay? The taxi example. Okay? Let's write the problem. Imagine you are driving a taxi that charges. What is going to be the charge? Let's say $2 per kilometer, okay, of distance traveled. Also, there is an initial charge of, let's say, $150, okay, $150, just for calling the taxi, right? When you call the taxi, when you enter in the taxi, even before you start moving, there's already some initial charge. So the count that indicates how much you should pay does not start from zero. It starts from, let's say, 150 and keeps going from there. There is an initial charge of 150, okay? So a client indicates a 10 kilometers, let's say a destination that is 10 kilometers. So a destination that is 10 kilometers away from us. Away, that's it. We want to cover the distance of 10 kilometers, okay? So let's indicate what we need to find here. First, what is the price that the client needs to pay for the trip B, if the price is Y, let's say, and the distance is X, write a formula for the price for any concrete distance. So basically what this asks us to do is, doesn't matter what the clients say. Like the first client for the day can say, drive me to this destination that is 10 kilometers away. Then the second client may say, drive me to another destination that is 5 kilometers away, okay? The third client will say, drive me to a different destination that is 20 kilometers away. So if the distance is X, doesn't matter what the concrete distance is, just how are we going to calculate the price given our charges and the distance being X, just in the general case, all right? And then the next task is write a formula for calculating the price for any taxi if the fees are A and B, the distance is X, and the price is Y. Okay, so what this asks us to do is basically what is the difference between B and C. So B tells us write the formula for your taxi. Okay, your taxi has fixed charges, $2 per kilometer and $1.50 initial charge. But if tomorrow I decide to drive another taxi or switch my job and go work for another taxi company, the taxi I'll be driving will have different charges. Maybe it's going to be $3 per kilometer, maybe it's going to be $1 initial charge, etc., etc. So if I denote this with A and B letters, all right, doesn't matter what the concrete charges are. Again, the price is X. The distance is X, the price is Y. How would I calculate the price for the trip, given that I'm driving any taxi with any kind of charges and the client may say any distance? Makes sense? All right. And this exercise is fairly simple and I think it's common sense. So solution A, Y equals to, so in our case we have $2 per kilometer times 10 kilometers of distance plus $1.50 initial charge. So the price for the trip in the concrete case will be 20 plus 1.5, which is $21.50, right? B, if the distance is X for our taxi, we are going to calculate the price by multiplying X by 2 and then adding the initial charge, right? And then C, if the initial charge is A, doesn't matter what it may be, I'll multiply it by the distance X and I add the charge for the initial charge. Okay, so it's going to be AX plus B. All right. So the first thing, the first formula here, the first calculation is an arithmetical calculation. So this is arithmetics. And those two here, they are algebraic formulas. Okay, algebraic. Okay, this is the difference. I think this example makes it clear. If I want to calculate some specific calculation with specific numbers, I'm dealing with arithmetics. If I want to calculate something in the general case, regardless of concrete numbers, I'm using algebraic formulas. Okay, so far so good? Good. Let's move on. Point 3. Constants and variables. Okay, so a constant, a letter which indicates a number whose value is assumed to be known. All right, very important, is assumed to be known in advance. And it doesn't change in the course of the problem or in general. So what does that mean? Okay, we are using constants very frequently when we're doing mathematics, and the simplest example of a constant is pi. All right, for example, pi, which is approximately, as you know, 3.14. Okay, when we are encountering pi, the letter pi, in some formula, we are not asking ourselves, wow, what is pi? How do we find pi, right? How do we calculate the value of this letter? No, we know what the value of this letter is. We know that it's approximately 3.14. We don't need to calculate. It's a letter, but this letter is associated with some concrete value. So therefore, we know what the value of the letter is in advance before we start solving the problem. Okay, this is a constant. Now, there are many more constants, like in higher grades, we'll study about the constant E, which is a natural constant, or yeah, I forgot the concrete name. We call it in Bulgarian Neperovo číslo, Neper's number or something like that. So this has approximately the value of 2.7. Okay, 2.7, etc., etc. It's like pi. When we see E in higher grades, we know that this is approximately 2.7. Okay, and there are other constants, etc., etc. So the speed of light, right? In the formula, Einstein's famous formula, E equals mc squared. C is a constant. C, the speed of light, which is what was it? 300,000 meters per second, right? 300,000 meters per second is the speed of light. No, actually, wait, kilometers per second. 300,000 kilometers per second. I made light very slow, etc., etc. These are numbers that we know in advance before start solving the problem. Now here we want to make another distinction. Universal constants pi, E, C, the speed of light in a vacuum, right? Etc., etc. So these are constants that do not change at all. Their associated value do not change at all. Okay, but now there is another type of constant, and that type of constant is called the parameter. Okay, parameters. We denote those with the first letters of the English alphabet. Okay, we denote them with the first letters of the English alphabet. For those of you who don't know what the first letters are, A, B, C, D, etc., etc. Okay, now these are constants. These are constants, but they change their values in different problems. So what does that mean? You know the basic equation with one unknown of the first degree, right? what later we'll call a linear equation. This is the equation ax plus b equals 0. Okay. Now these letters here, a and b, they are parameters. Because first of all, we know their value in advance. So the problem will be concrete problem. For example, 2x plus 1 equals 0. Okay, so a equals 2, b equals 1. But then we solve this, and then the next problem will be, for example, 3x minus 5 equals 0. So a equals 3, b equals minus 5. Okay, so they're constants. Parameters are constants because we know their value in advance before start solving the problem. Before we start solving this equation, we know that a is 2, b is 1. Before start solving this equation, we know that a is 3 and b is minus 5. Okay, so parameters count as constants, but they're different from universal constants like pi. Pi is always going to be 3.14, right? But these parameters, they change in every concrete problem. In one case, a is 2. In the next problem, a is 3. In one problem, b is 1. In the next problem, b is minus 5, etc., etc. So they change in every problem. Okay, but we know them, so they're constants. Makes sense? And then the next thing here, so B, C, D, variables. Okay. Letters, we denote them with the last letters of the English alphabet, X, Y, Z, etc., etc. Maybe U, maybe T, maybe W, maybe V, doesn't matter. The last letters of the English alphabet, whose value is unknown, and we need to find it by solving the equation, or the problem, doesn't matter, equation. Let's give some examples. So ax plus b equals 0. Obviously x is a variable. What about the formula for the area of the circle? The area is pi r squared. So pi is a constant, r and a will be variables. Now in this case, a is like the first letter of the English alphabet, but we just orientate ourselves, like we figure out which is a constant, which is a variable, by asking ourselves, do we know it in advance? Do we know it before start solving the problem? And obviously no, right? We need to, if we have a circle, we need to measure the radius. So we have to figure out what the radius is, then we have to calculate the area, etc., etc. So they are not parameters. Okay. Okay. Now the next thing, for dependent and independent variables. An independent variable is one whose value we discover first, and its discovery does not depend on knowing other variables. A dependent variable is one whose calculation depends on knowing other variables first. Okay, what does that mean? Let me give you an example. So, okay, the taxi example. Okay, the taxi example was y equals ax plus b, right? So, the charges a and b are known in advance. If I'm driving the taxi, before I take on the client, I know, and the client knows also, because these charges are written on the window of the taxi, how much is the per kilometer charge and how much is the initial charge. Okay, so both parties know those charges in advance. These are parameters. They can change for various taxis, but they're known parameters. Now x and y are variables. X and y are variables, because I see the client approaching, right, and I don't know in advance how far away a destination the client is going to ask us to drive him to, right? He can say 10 kilometers, maybe 15, maybe 20. And therefore, I don't know in advance, obviously, how much the price of the trip will be, how much profit I'll make from that trip. But now the question is, which of the two variables I will know in advance, x or y? Do I learn the distance first and then calculate the price of the trip, or do I learn the price of the trip first and then I calculate the distance to the destination? Well, obviously, I learn the distance first, right? The client tells me, drive me to this location 10 kilometers away, and then I can calculate by using this formula. I can calculate how much the price will be for the trip. Okay, so in this case we call x an independent variable, and therefore y is a dependent variable. Okay, I need to learn the distance first, and then I can calculate the price. I cannot calculate the price without knowing the distance, but I don't need to know the price in order to discover the distance. The distance is simply told to me by the client directly. Me discovering the distance does not depend on knowing anything else. Okay, this is why x indicating the distance is an independent variable, and why the price of the trip is a dependent variable. So far so good. Another example, again, a equals pi r squared. This is a constant. Now r and a are variables, and again, which of these two variables do I discover first? Do I find the radius first and then calculate the area of the circle? Or do I find the area first and then I calculate the radius? Obviously, it's much easier to just take a ruler, go measure the radius, which is just a straight line. Just measure this radius with the ruler, and this is how you discover it directly, and then you plug in the numbers and find the area of the circle. How would you calculate the area directly of the circle? Well, that's going to be very, very difficult, right? How do you do it? Write me in the comments below, how would you discover if I just draw your circle like this. Okay, this is the center, this is the radius. How would you calculate the area directly and then finding the radius? Let me know in the comments below, okay? So R is independent. I just take the ruler, measure it, 5 centimeters, great. I know its value independently of anything else. I plug in the numbers and find A. So A will be dependent. Okay, makes sense? Okay. All right, so far so good. Let's move on. The next thing we want to consider is what is a rational expression. So this is number 5 here. A rational expression. Okay. An algebraic expression which consists of constants, variables, and parameters, assuming rational values. Okay. A rational expression is just think of any combination of numbers and letters and plus and minuses and multiplication and division, and that's your rational expression, okay? Just throw in some numbers and it counts as a rational expression. So throw in some letters and numbers. So this is A, this is a rational expression. ABC minus x squared y over z. Okay, I'm just throwing random numbers. Let's call this B. A squared b to the power of 3 x to the power of 2 plus a times d minus y squared over z to the power of 4. Okay, just any combination, doesn't matter. It's a rational expression. Okay. Next, a whole rational expression this is a rational expression which does not involve a variable in the denominator. Okay, so for example, if I have this expression abx to the power of 2 plus 3 xy to the power of 3 minus z over 10. Okay, I'm just making some numbers up. This is a whole expression. If I have, for example, xy over ab plus z over 2c, okay? Now, because I count a, b, and c as numbers, as known numbers, as parameters, this also is going to be a whole rational expression. Okay? But if I have this one, axy over 2z, okay, this is not a whole expression, because I'm counting the z as a variable, okay, variable. And therefore, if I have a variable in the denominator, it's not a whole expression. I can have a number, I can have a parameter, a constant, it's fine. But a variable x, y, z, etc. is not fine, okay? If I have a variable, it's not a whole expression. Makes sense? Okay, good. And now finally, we are ready to define what a monomial is. So a monomial, a whole rational expression which involves only multiplication, obviously division as well, because division is a type of multiplication by a fraction, of constants and variables. By constants I include parameters, obviously, so constants, parameters and variables. Alright, this is the monomial. Now let's give some examples. If I have a to the power of 2, b, c, x squared over d, okay, is a monomial. I have only multiplication of constants and variables, because this whole thing here is a constant. Is a constant multiplied by variable x squared, alright? So is a monomial if I have a squared bc x squared over y. Not a monomial because it's not a whole expression. This is a variable. Not a monomial, not a whole expression. If I have, for example, let's say ax plus b, not a monomial, because I have an addition. If I want to have a monomial, it's only multiplication, okay? But if I have c, a plus b times x, this is a monomial. Because this here, if I'm adding two numbers, I get a number. So this is a constant, a number, and this is a variable. So I have a multiplication between a constant and a variable. But in the previous example, I had addition between a monomial and another constant. So this was not a monomial itself, but this one in C is, I have a constant times a variable, okay? A plus b counted as a single number, okay? Because basically I'm adding two numbers. Like if I have, for example, 4 minus 1/2 times x. Now obviously this is going to be 3.5 times x, a monomial. Remember that we count constants and parameters in the same way as we treat numbers, okay? Variables are treated differently, okay? What about, is the number 2, is 2 a monomial? Yes, 2 is a monomial. Why? Why is it a monomial? By definition, the monomial has to be a product of a constant and a variable. So the constant is 2. Where is the variable? Well, I can always add the variable like this. 2 equals 2 times 1, and 1 is 2 times x to the power of 0. X to the power of 0 is 1. Well, technically I still have just a number, 2 times 1. Now I'm including a variable. Doesn't matter that it's to the power of 0. If I have x, it's a variable to the power of 0. It's still a variable. Alright, so I have a constant here, constant, times a variable. That makes it a monomial by definition. Alright, A, B, C, D, E, F. What about, is x a monomial? Yes, obviously. How do I add the constant? I add 1. X equals 1 times x. This is a variable and this is a constant. Okay, so by definition, again, it is a monomial. Good. Okay, so far so good. Now let's do some exercises, shall we? Okay, this exercise here asks us to indicate whether the given expressions are whole expressions or they're not whole expression. Okay, the first one, is it a whole expression? When we ask for whole expressions, we want to know, is there a variable in the denominator? So we don't see any variable in the denominator, and therefore this is yes, this is a whole expression. What about here? No variable in the denominator, so yes, this is yes. What about here? Again, no variable in the denominator, so this is yes. What about here? There is a variable denominator, no. Okay, these are whole expression. The last one is not. Here, no. Here, yes. A, we count it as a constant, as a number. It's not a variable, so this is a whole expression. Here, no. And the last one, no. Okay. Good. So far, so good. Okay. In this exercise, the first one, we want to answer for each of these expressions, is it a monomial or not? In other words, do we have only multiplication of constants and variables or not? All right. So let's see. The first one, kx, is kx a monomial? Obviously, yes. What did I choose here? Need to choose this. Nope. Can I choose this? Yeah, okay. Alright, so this is yes. What about 2a plus x? I have a plus here, no. What about x? Yes. A to the power of 5? Yes. Why is a to the power of 5? Because I can multiply by x to the power of 0. I have a constant times a variable. What about here? 2x to the power of 3 times minus y. Yes, obviously I have 2 times x to the power of 3 times minus 1 times y. So only multiplication of constants and variables. Is 1 a monomial? Yes. Is a monomial? Yes. 8 times x to the power of 0. X to the power of 3 times y to the power of 3 times minus 1. This is yes. I'm just multiplying constants and variables. 1/5 minus 4. Well, this is minus 3 and 4/5. So this is a constant here. Times some variables. Obviously, yes. And 4 plus x. Is 4 plus x a monomial? No. I'm adding two expressions, so this is not a monomial. Makes sense so far? Okay, you can review these exercises later if you want to try again for yourself. We want to know what is the standard form of a monomial. Two conditions have to be met. Okay, the first condition is we want only one constant written in the beginning of the expression, and the second condition is we want to have only one letter for each variable. Okay, so what does that mean? For example, if I have this monomial 2 times x times 3 times y, okay, what is the problem here? I have two different constants. I have two different numbers that I am multiplying, and this is not in standard form. Not in standard form. To make it into a standard form, I just need to multiply those constants in order to have only one constant written in the beginning. So if I have 6xy, this is in standard form. Makes sense? Okay. What about this one? 2xy xz. Okay. Why is this not in standard form? In standard form, well, because I want to I have two x letters. Okay, I don't want to have x times x. I want only one letter for each variable, so I don't want to have any repeating letters. So I just multiply again x times x, and I get 2x squared yz in standard form. So basically the standard form is the most simplified version of the expression. It makes sense? Okay. Now let's do another exercise very quickly. How do we write these expressions in standard form? So the first one, 9x to the power of 3 times x times y to the power of 2. I write it here. So a is going to be 9x to the power of 4. Okay, 3 plus 1 is 4. Y to the power of 2. The next one, so I have 1x here, 1x here, y here, and y to the power of 2. So the next one will be 3x squared, x squared, y to the power of 3, okay, and z. Okay, this is my standard form. The next one, let's see, I have x to the power of 2, x to the power of 2, z and z. Okay, so the next one will be 6 over 7, x to the power of 4, y to the power of 3, and z to the power of 2. Okay, good. What about b? I multiply the constants here. 3 times minus 2, this is minus 6. X times x is x to the power of 2, y to the power of 2. Okay. Next one, remember the constant has to be in front of the expression, so this has to come here in order to have the standard form. So the next one will be just minus x to the power of 3 y. Okay, and here again minus 1 times minus 3, this is 3 x to the power of 3 and z. Okay, these are my standard forms for this exercise. If you have any questions, again, let me know in the comments below. All right, the coefficient of a monomial, the constant of the monomial in standard form. Okay, in standard form. Let's give some examples. So if I have 2ax squared y to the power of 3, now because a I count it as a parameter, it's going to be part of the constant. So this thing here is my constant. So coefficient is equal to 2a, right? If I have, for example, this expression here, 3 over 5b, that doesn't matter what it is, times x to the power 2 times 7 times y. So first I need to write it in standard form. I need to multiply these constants here. So b equals 21 over 5bx squared y, and then this is going to be the coefficient. So coefficient is equal to 21 over 5b, okay, and so on and so forth. Makes sense? Just the constant in front of the expression after you write it in standard form. Let's do some more exercises. Again, if x and y are the variables, a and b are the parameters, what is the coefficient for each expression? So a, I'll write them here, the coefficient is 7, okay. The next one has a coefficient of 1. This is the constant. Here I always need a constant. Remember, in order to have a monomial, I always need a constant. If there is no constant, means the constant is just 1. So the second is 1. Here is minus 1. And here is 1/2. Okay. So these are for A. For B now is 1/2 again. This is the constant. I'm multiplying. So this is 1/2 times x times y. So the constant is 1/2. Here is 3/4. And here, this whole thing I will take as the coefficient. So 2ab over 3 is the coefficient. And here this whole thing is the coefficient. So this is 5a over 3. Makes sense? Okay, good. I don't think it's very difficult, but practice on your own. The degree of the monomial, this is the sum of the degrees of the variables. Okay, so for example, a equals 2ax squared y to the power of 3z. All right, so the degree of a is going to be, I add up the degrees of the variables, 2 plus 3, and here is 1. 2 plus 3 plus 1 is 6. Okay, so this monomial is of degree 6. So far so good. If I have let's say b is, let's say, 3a squared b to the power of 3x y. Okay, so be careful that we want to sum the degrees only of the variables. Remember, the parameters are part of the coefficient. They don't count in calculating the degree. So this thing here is my coefficient, and the degree is just 1 plus 1 is 2. So degree of b equals 2. I don't add 2 and 3 of the degrees of the constants in calculating the degree of the monomial. Okay, only the degrees of the variables count in the sum. So what are the degrees for each of these monomials? Okay, so for A, first 2 plus 1 is 3, okay, then 3 again, 1, 1 plus 1 plus 1 is 3, 3B, so 3 plus 2, 5, I don't count the A, so 2 plus 4 is 6, I don't count 2 to the power of 2 in the degree, so 2 plus 1 plus 2, this is 5 again. Makes sense? And finally, the last exercise for today is number 5. So this exercise asks us to write in standard form and calculate the value of the expression. So let's do it together very quickly. So what is A in standard form? I multiply 2 times 3 is 6, x times x squared is x to the power of 3, and I'll just substitute for this one. If x equals 2, I have 2 to the power of 3 is 8, times 6 is 48, and I'll skip the others. For B, let me write it here. So B equals, I multiply minus 2 thirds times 3, 3 and 3 will cancel, I get minus 2a, x to the power of 3. So if a is minus 4, minus 2 times minus 4 times minus 3 halves to the power of 3. So this is minus times minus is plus 8. The minus here is preserved because of the third power. So I have minus 27 over 8, cancel, and I get minus 27. Okay, so far so good. And then for the last one, C, I'll do, what do I have here? 4/5, minus, so the minus will come in front, x to the power of 3, y to the power of 2, and I substitute here, I get minus 4 over 5. So x is minus 1, minus 1 to the power of 3 is again minus 1, and 1 half, 0.5 is 1 half to the power of 2 is 1/4. Okay, so this and this will cancel, and minus times minus is a plus, so 1 over 5, which is 0.2. Okay, all right, and that's going to be it for today. We've got approximately an hour. This is the longest show I've ever done so far. If you have any questions, let me know. I know that we've covered lots of material today. I hope it makes sense for you. This is a fundamental topic. The monomial is a fundamental concept to be understood when we want to advance into algebra. Next time we're going to continue with the monomial, because if you thought this is everything, no, we are far from discussing everything about the monomial. We haven't discussed how to add monomials, how to multiply them, what are similar monomials, and etc, etc. So next time we're going to cover another show. We're going to devote another show to the topic of monomials. This is how important this topic is, guys. Okay, thank you very much. Like and subscribe, and I'll see you in the next one. Bye for now.